Welcome to Swayam Prabha series in computer science. This is a course on artificial intelligence and we are towards the end of the course and this is the last session. So, in this session I will just give you a gist of whatever we did on the last 39 sessions as in a nutshell and where we can apply all our skills. So, when we started off with a mathematical representation of how to represent a problem. Generally an AI problem we have to give, see, for a machine we have to give everything mathematically. So, in order to have a proper formulation, this is called as a problem formulation method. We started off with the states. The state can either that can have a true or false value and it has to be at that particular instant, that is called as a state. So, in this, if you look at this diagram, this we have used earlier in our earlier sessions. We start with some state and the initial state we called as S0. We apply the successor function or action, it can go to the next state and it can go to the next state until we reach to the goal as Sn. So, the total number of states, initial state, final state and action. If we are able to represent a problem in this fashion, then it becomes easier in order to put it into an AI perspective in the first level where we started off with searches. In addition to these four representation, we would also have as cost. The cost in terms of some number, say it can be a distance or it can be a cost as in say US dollars or rupees, some type of quantification that we are considering as a cost or as a heuristic value. Now, having the representation in this form, then we went into different kind of search techniques of uninformed and informed search. And uninformed search is something where you start at some point and we just explore until we reach to the goal. We do not know where the goal is, but we explore. That is the uninformed search. Whereas informed search is at the starting point S0, we know where the goal is by some means, and that some means we are calling it as a heuristic value. Suppose we know the somewhere by experiment data or through some other means the goal, we can focus through that path in order to reach. That is called as an informed search. So, under uninformed search, we have these searches that we have as a part of first unit that we did. The first is the breadth first search, where the search goes in breadth wise like this. It will go into start with S0, goes A, B, C, D and move on to the next level. In depth first search, it would go depth wise. The uniform cost search, it is based on the cost wise, it would go deeper based on the distance cost here. And the depth limited, we will assign a limit to the depth and within that limit the search happens. Iterative deepening, with respect to the depth limited, it will go in breadth wise at each stage. So, these are the different uninformed techniques that we did, and with informed level we went into the greedy best first search, A star algorithm, hill climbing and simulated annealing. Apart from these searches, we also did something on constraint satisfaction problem. We call this as CSP, abbreviated as CSP, constraint satisfaction problem as CSP, and also we did on game search or adversarial search. A summary of the uninformed search techniques of different parameters we have seen. The four parameters that are essential are completeness, whether given a point where are we able to completely get the goal perspective. If you start at some point, are we able to achieve the goal, that is complete. What is the quickest time possible, what is the efficient space that is occupying the search and is it optimal. These are the four parameters, and for various search techniques we have analyzed it through these parameters. And for informed search we had this evaluation formula as f of n, as g of n is the straight distance cost, is the actual cost, and h of n is the heuristic cost. So, if we take uniform cost search, we are saying h of n is going to be 0. So, f of n is actually equal to g of n, which is the actual cost. In the greedy best first search, we will only worry about the h of n, leaving out g of n. For A star, it is optimal because we have both g of n plus h of n. So, this comes under the informed search category. In the CSP, which is the constraint satisfaction problems, we formulated according to the variables, domains and constraints, where variables, if you take the example of map coloring problem, we have the color map of Australia, where the variables are the different regions like W, A, N, T, Q, NSW, V, SA and T. If you see here, these are the different variables. The domains that are to be colored are red, green and blue, and through this we are giving the constraint such that adjacent regions should not have the same color. So, if we specify the constraints with respect to domains and variables, can we get a solution according to this? So, that is part of the CSP formulation. Again, it is a search technique that we did. Another technique was the game search, which happens across two individuals or persons or agents, and that happens according to the particular heuristic value. And then we moved on to the next unit, where we said apart from the search technique, we can get into the logical portion of AI. And why logic? Because of the reasoning aspect, and the reasoning aspect is very common in human beings. The reasoning in the sense the answering the question why. So, in that case, can a machine reason out? And in order to reason out, again we will go back to a mathematics. Pretty much it is in the form of the discrete math. And in discrete math, there are two basic logical portions. One is proposition, another one is predicate. So, in the proposition logic, if you see, the syntax is going to be atomic propositions and the connectives, and along with that, if you see an example of a proposition logic, P and Q implies not R, that and P or Q implies R. These are some proposition formulas, and the semantics is the truth tables for all these. An example would be it is raining, we can just mark it as P. And using these we have different reasoning methods that are available using the rules like modus ponens, tollens, syllogism, universal generalization and so on. So, using these reasoning methods we can ask a machine to reason out, given, see again, given some statements, can conclusion be derived. For that we are going to use both proposition as well as predicate logic. When compared proposition with predicate, only two things vary. One is the quantifiers, and because of quantifiers we would have functions and predicates. This we did in detail in unit 2. Now, in the semantics, it would be very similar to the syntax. Apart from that, we have the interpretation here, and the domain, when we call it, is with respect to the interpretation in terms of domain and I that maps object functions from this point. So, and some examples of predicate logic are given, like all humans are mortal can be expressed like this. So, predicate logic is in one way much richer than proposition logic, such that we can add more quantifying terms in predicate logic. So, we have through this the reasoning process can be developed in a machine. So one type of reasoning that we did is through resolution, and that's for an automated theorem proving that was used in AI. So this comes in unit 2 where we did with logic, and using logic the third unit where we specified is the knowledge representation, where in the knowledge representation apart from object oriented approach we saw about three types. One is the semantic network, frames and ontologies. In the semantic network, if you see, it is just, this is an example that is given in the animal world. The same example we have seen in one session where mammal is an animal, dog is an animal, tail has a part dog. So we can express a short statements like this, is a kind or can fly. So this statements, a single verb kind of simple sentences format can be expressed in a tree like structure that can be given in the semantic networks. The advantage with this approach is that it can be logically expressed as a proposition or predicate logic, and once we express in the predicate or proposition logic the reasoning becomes easier. So that is the reason why the semantic network knowledge representation is effective. But there are some difficulty in semantic networks. Small difficulty is representation of nodes. Nodes, whether it is cat or one specific instance may be Alice is a cat. If we say that, then that also will have a similar node. So this disadvantage will be rectified in terms of frames. In frames we would have, apart from the nodes, we have some other properties. The properties are like the slots and the fillers. This side is the slots and the filler size. Say for example, this is an example for vehicle domain where there is a vehicle, there are 4 wheels in a vehicle, it has engine, petrol is the fuel type. So we can mention the parts in the fillers according to the slots in the type of car. We can specify different frame structure like this. So that is not possible in semantic networks. So the some applications of frames would be, can be seen in expert systems, planning and configuration of some machines or some industrial oriented systems, and the natural language understanding. Now there are some difficulties in frames, so we went in for ontologies, the third step, where in ontology this is an example of say university world which we did earlier in one of the sessions, where in addition to the properties here there are more varieties here where we can specify the data properties, whether it is a string, integer, all these, and the data property, object property, whether it is a subclass, all these here we cannot mention, but say in frames we cannot mention all that, but in ontology we can have several types that can be included, and this is much more richer than frames or semantic networks. So if we combine all the three, now where to use which application, again it depends on the user type. Say is in semantic network it is very simple, and ontologies it is formal, rich, and we can reason out. And we also did one session here on demo of ontology using the tool of Protige. So and together all the three, including the object oriented, they represent knowledge, and using these three we can share and reuse the knowledge in more efficient way, and especially the ontology we can use it to infer. Then we moved on to the natural language processing, which is in unit 5, where it combines computers to understand, interpret and generate human language. We started off with morphology in the sense where we talked about the words, simple words like suppose you take one word like unhappiness. We have un as a prefix, happy as the root, and ness as the suffix. Say another example would be play, played, play as the root and ed. So when we deal with morphology, can a computer program understand what is the root and attach the prefix and suffix to itself, or given a word, can the root be extracted? So those tasks we did earlier, that is the starting point of the natural language processing. Some NLP task here would be tokenization, stemming. Tokenization is given into specific tokens, like we have had enough discussion on tokenizing part. The stemming is giving out the particular root value of it. Lemmatization, adding up the prefix or suffixes. Part of speech tagging, suppose if it is happy, the part of speech is adjective. Morphological analysis, how each with happy only ness will be included, other portions may not be happy, will not come. So how to identify those aspects of it, we have seen in morphology portion. So one example, the cats chased the mice in the garden. Here if we tokenize, stem, lemmatize, those portions will get into the morphology. Now once that word portion is done, we moved into the syntactic portion where we worked out with the different part of speech, phrases, the grammatical structure, and the parse tree. If you look at this parse tree, we have had 1 or 2 sessions only on this parse tree. And why do we need that? Because much of the task, the NLP task, syntactically can be addressed at this level itself, the parse tree itself. Suppose you say the cats chased the mice in the garden. We can draw a parse tree, and through this parse tree we can say whether this statement, the cats chased the mice in the garden, is actually correct or not. And it can also be used for ambiguous representation. If you remember the statement that we did, John saw the person through the telescope with eyes. So those had 2 different interpretations that can be addressed through this type of parse tree. Another view is the dependency parse tree that also we have seen. And once we have done the syntax, we moved into the semantics portion of it. The semantics considered the word meaning, the sentence meaning, the logical form of it in addition to the relation between them. So suppose in the logical form, we have cats chase mice, and where it is located? In the garden. So the same representation, the cats chase the mice in the garden, in the logical representation we can give it in this form. And the word sense, we did number of examples in the semantics where if it is big, the synonym can be used as large. So how do we, a machine, understand that big and large are same? It's through the relation of synonym. And similarly, hot, cold as antonym, dog, animal as hyponym, meronym and role. All these different names we are addressing through the semantic structure. In common NLP tasks that will be using semantics are word sense disambiguation or role labeling, named entity. Word sense disambiguation, for example, bank. Bank used to mean 2 things. One, the river bank, and the other one is the normal financial bank. Named entity recognition, in the sense the person Mr. Ram. So that Mr. Ram represents a person. So those are the location Delhi. Those things are represented as name entity recognition. Then the textual entailment, what one phrase leads to the other, the parsing and the concept relation, all these are going to be some of the key NLP applications that can be addressed to the semantics side. Now moving towards from the semantics to the pragmatics is the actual day-to-day conversation that we see. Say the focus is the speaker intent, what the one speaker is speaking and the other speaker is listening. So what is the conversation that is happening? Can one get the conversation without knowing the details? For example, if on a bus when you travel you hear another 2 persons talking, and can you get the idea of what 2 persons are talking? So those are the real world examples of the pragmatics. Another example that we have given here is, can you pass the salt? And the reply is understood in the context as agreement and instant to act. So this is the actually what it is meaning according to these 2 statements. Can you pass the salt? And sure. One person say is, can you pass? And second says yes, very sure. So, this is the meaning with which we understand. So, another example is I will meet you at the bank, the same thing I specified before. The third is the pragmatic phenomena, where there are presuppositions, speech act or discourse. And the NLP task, the applications with respect to pragmatics is intent, dialogue, co-reference resolution. This co-reference is something like what we did in the previous session. Where does it refer to? So, where is France located, and the next statement it. So, that is it referring to France, that is co-reference. And the discourse analysis, like I specified, in the real world, what is the type of, when two persons are talking, what is it all about? So, those kind of abstract views are the discourse. The sentiment, whether it is someone is saying positive or negative, and we did this sentiment as an example in prompt and in the question answering session. So, these are some NLP tasks where the pragmatics are being used. And in a nutshell, if you see, there are raw text, the cats chase the mice, we tokenize, lematize, where we break it into separate words. There is a parse structure to it, the context, which is the syntactic structure, and we derive the meaning out of it, the entities and relation, interpret it, use the context and knowledge apart from the syntactic structure and the semantic structure, and are we able to understand the meaning correctly. Cats are chasing mice, where in the location of garden, can we understand it? So, this is the entire pipeline of natural language processing. Say we have seen this in detail, but in the recent trends, those are not sufficient enough for the machines to understand the natural language. So, we went into the statistical language processing, where we have seen some of the techniques like naive Bayes, probabilistic context free grammar and hidden Markov model. And along with it, we have also seen the cosine similarity or term frequency, which it will be helpful for converting those the word to some numbers and finding out the similarity structure in terms of cosine similarity, and term frequency and inverse document frequency. Again, through that we will be able to identify which are going to be similar and which to be not to be counted. And from that we move to some kind of embeddings. Embeddings are needed in order to understand the structure of a sentence, and here moved into the BERT structure of it, but I have mentioned it here. We did some neural networks where most of the embeddings are dealt with the training with neural network side, so that the idea is in a sentence, and we did the sentence, say suppose the cat jumped and the dog jumped. Ideally, we want to say that cat and dog are very similar because it belongs to some category of animals. So, can we have a vector representation of cat and dog to be very similar in the sense, in the same, suppose if it is cat and dog, it has to appear only similar. So, the vector should actually appear similar. So, that is the focus with which we built, say the BERT was built, and in the sense we also discussed embeddings with respect to it. So, how the embeddings are developed and how the LLMs are able to predict the next word or the next statement, we did in statistical natural language processing, and moving towards the generative AI side. And in the generative AI side, we did the different components of prompt engineering. We started off with D for directive, and then role. If we add role to the prompt, what would happen? Then the context or the background information with audience information or the relevance of data, how the prompt structure would improve. Then in addition to that, we gave the examples for E, and the format or the output, how the response should be from the LLM. So, those things we did with the components and within the prompt structure, and also we have seen the different types of prompt like zero shot or one shot or chain of thought or tree of thought or graph of thought, TOT, graph of thought. So, we have seen some examples of it. we have seen both the theoretical side as well as the practical side of implementation of those in well. And moving from prompt to agent. So, the difference between prompt and agent, prompt is just one instruction, LLM one instruction, LLM does the task and give the response. In multi-agent, it is a series of actions and then the response. This is actually the particular goal that we derive for a single agent. And we have also seen the different types of agent like stateless agent, stateful agent, tool using agent, and say the goal oriented agent. In multi-agent, we have seen 2 or 3 patterns of it. One is pipelining, another one is with parallel agent, and another pattern with plan and executable agent, and plan with executable with say the other critique agent. Also we have seen some examples of it, and that is the whole course what we have covered so far. And if you look at the bigger picture, so the AI is about philosophy, where we involve the Greek philosophy of the logic. It involves mathematics, pretty much it has probability and statistics, the logical portion coming into it, the discrete math. It has the psychology, how humans understand and converse, linguistic portion of it like NLP task, NLP syntactic portion of it, we got it from the linguistics, the neuroscience aspect of it from the neural networks, basically from that point of view. And of course, because of coding, it is a computer science. So, this is the slide we gave during the first session, and it is coming back just to give you the full-fledged view of where AI stands and where are the applications. And if you look at this slide, actually AI is at the top. You will be having another course on machine learning and also deep learning. AI is the full-fledged course. And on the right side, there are some applications of it like medical diagnosis, stock market trading. These are some applications where you can apply, and there are other applications also right now where you can look, and whatever you do, please do it carefully with AI and use it ethically. And all the references for this course is from Stuart Russell and Peter Norvik's book, AI book, 3rd and 4th edition, and some of it I have got the images from Gemini and ChatGPT, and some I have also referred it to Qwen LLM. The coding base I have used mostly the Google Colab. Thank you.